Good evening. Thank you for joining my talk about transforming your perception on text generation. My name is Kerkdijk. I'm a managing consultant at Open Circle Solutions, a small boutique consultancy company in Eindhoven. We mostly work with big companies. For example, Brand Loyalty, the Royal Dutch Navy, Randstad Global, and on the moment I'm working for IKEA. Within this talk, we're going to look into the new concepts within NLP. One of the major changes from the last years is attention. From here on, we're going to talk about attention and the way to it. When you look into NLP, you should see there are two approaches on the moment. The classic feed-forward neural networks and the recurrent neural networks. When you're using feed-forward neural network, you can only look into the next words. So your prediction is only about the next word within a sentence you want to generate. The problem with this is you cannot go back in time. When the network predicts a specific word and the context changes, for example, you want to talk about dogs instead of cats, it's really hard to come back to it from it. When you use a recurrent neural network, the network is reflective. So with every prediction, it can go back in time and find new ways to come to a prediction. One of the most used approaches when using recurrent neural networks are sequence-to-sequence models. Sequence-to-sequence models are using an encoder to process the input sequence and compress the information into a context vector. So this context vector is mostly of a fixed length. This representation is expected to be a good summary of the meaning of the whole source sequence. In the end of the model, there is a decoder. The decoder is initialized with the context vector to emit the transform output. This kind of models are also called encoder-decoder models. When the encoder is encoding the sentence, it looks into the distribution of words that's following up into your corpus. The decoder tries to predict what will be the next word. If you look into these two distributions, you see that in a peaked distribution, we can see right away, or even the decoder can predict what will be the next word, hot. But in a flat distribution, it's not that clear. The certainty about which word is relatively low. This all has to do with it only looks at never in a recurrent neural network and not over the whole scope, mostly. This has to do with the idea that recurrent neural networks only can look for a fixed length context vector. The fixed length content vector means that if you train on corpus, for example, length 8, it only can predict on length 8. If you can see also over here, what's wrong with the sequence-to-sequence, it forgets after the party is learned to. So if you want to generate a sentence of length 9 and you only trained on 8, it will forget the first spot once it's completed the process. This is a big problem and is solved by the attention mechanism. The attention mechanism is an intermediate layer that you put between the encoder and the decoder. This layer parameterized a simple way to put attention to a couple of words within the sentence that has the highest meaning. So the secret sauce is to create shortcuts between the contents vector and the entire source input. These weights of these shortcut connections are customizable for each output element. The scientific definition of this attention layer is given by the following slides. For example, we have an input with a given length x, sequence length x with a length n. The output is a sequence given by I with length m. For this, we want to look into the attention we need. By encoding with an, for example, bidirectional RNN, with a forward hidden state and a backward one that also reflects on it, a simple concatenation of two represented encoder states can be found. Then in the decoder using a so-called context vector for an output giving I. After this output context vector is made, it will try to align the score, the expected scores between two words, IT and XI. After this alignment, it may have converted to a softmax, so neural networks can work with it. So every score will be between 0 and 1. After alignment, you predict the score. The score function is mostly a TAN function, but so it uses a nonlinear activation function. If you look over here, you see a correlation matrix of a given translation. The translation is between English and French. The higher the correlation, the more important the words are for the attention model. So over here, you see an example of a sequence-to-sequence model with attention in it. The encoder puts the corpus in. After that, the in-between layer of attention puts context to it, and the decoder put it in the right order. Over here, you see a variation on the attention model called self-attention. The self-attention mechanism relates different positions of a single sequence in order to compute a representation of the same sequence. So for example, it starts with T. After T, it looks in FBI and sees that FBI is in that sense more important. Afterwards, it looks at is, and so on and so on. In the end, you see that chasing, criminal, and run are the words they put attention in. They put attention on. In general, two variations on attention are mostly used. The one is called global attention, and the other is called local attention. Different is that global attention used an attention span over the whole sentence, where local attention only used an attention layer on aligned position and three words before or after that position. The whole idea is that using a global attention will fit one attention span over one sentence, where you give a limit local attention, variation of putting in more attentions in one sentence. The first one is mostly for very big corpus, and the second one is mostly for smaller corpus. The attention mechanism is using two kinds of mechanisms. The content-based addressed mechanism. The content addressed creates mostly attention factors based on similarity between the key factors extracted by the controller. Location-based addressing mostly used location-based addressing sums up at the values at different positions in the attention factor, weighted by a weighted distribution over the allowable integer shifts. Over here, you see the whole states. The previous state is loaded into the vector, where also the memory is. The last attention factor is used to interpolate between the in-memory content addressing and the gated convolutional shift, also called the location-based shift, where we discussed in the last slides. After these calculations, they are doing a sharpening. The sharpening is to fed the last attention factor again with the next following iteration on the word factor. By using self-attention, we can stack up, for example, in transformers, stack neural network, several layers. These layers help to minimize the number of parameters used into the model. If we had more time, I will discuss more about the transformer model. Sadly, our time is now over. Are there any questions?